So thank you for the introduction. My name is Brice, and I'm a student here at Queen Mary University of London in the Advanced Robotics group. I'm doing a PhD co-sponsored by the Shadow Robot company, and in this context, I've implemented the GRIP software framework that I'm going to present in this short talk. So robotic grasping and manipulation skills are required in a lot of use cases, ranging from autonomous pick and place of arbitrary objects to human-robot interaction. So robotic grasping is an active field of research, and researchers propose new solutions related to hardware and software. And unfortunately, it's quite difficult to decide which component we're going to use in a robotic system just based on a paper, right? We usually want to deploy them and then try to see, oh yes, this tactile sensor, for instance, is working fine for my use case with my expectation of what the system is supposed to do. So for this reason, we've implemented the GRIP software framework, which is a ROS-based, robot-agnostic open source software framework to quickly and easily design robot manipulation tasks with integrated components. So as you can see from the right-hand side diagram in here, we've implemented non-mutually exclusive ways to integrate software and hardware components. So for instance, you can use Moveit to interface your own robot directly from a Moveit package that you might have already to GRIP, or use launch files that are usually provided by the manufacturers to start or launch a robot or a sensor. You can also integrate the components to GRIP with minimal overhead. So to make things quite easy for users, we created a graphical interface that guides the users from robot integration, so the first step, to task design and execution. So before going any further, I want to highlight that this is not meant to be an optimized and high performance pipeline, because we know that labs and companies already have their own pipeline that are fully optimized for the use cases. So the whole point of this tool is rather to facilitate the integration of third parties components with minimal overhead. And then once we have proofs that a given component is working fine, then we'll be able to integrate it later on. So here on the right-hand side, you can see some of the reactive mechanisms we implemented in the robot configuration part. So for instance, red signals stating that some bit is wrong, or auto-completion. And so we've tuned the whole tool for really robotic grasping manipulation. So for instance, you have a generator of trajectories. So instead of generating the trajectory message manually, which can be a bit painful, you can define joint states in another editor and use these joint states to create a trajectory by saying, oh, I want my robots to go from this joint state to this one and this one, given a certain amount of time, so interpolation time and pause for each step. Here on the left-hand side, it shows how we're going to program the robot. So instead of having a standard textual programming paradigm, we opted for graphical programming paradigm because it doesn't require a user to know a specific language, such as Python or C++. So once the integration part is done, we'll have some states here that you'll be able to drag and drop to program the robot. So creating a task consists of drag and dropping the states or state machines in the main window, configuring each state through a simple to use interface, and connecting the outcomes of the different building blocks to define what should be executed depending on the result of their own executions. So in other words, you can create very adaptive behaviors of the robots quite easily without knowing how to program in Python, C++, or another language, depending on the data captured from sensors, for instance. So GRIP features a set of state and state machines that you can already use, but you can also add the new elements, and the whole documentation is there to help you through these steps. So GRIP has been already deployed in a lot of different use cases and environments, but here I've selected one that is quite related to merging data coming from different sensors and how it's easy to integrate everything. So here for this use case, it took, by a naive user, approximately 30 minutes to do the whole task. So we had already a vision-based grasping algorithm that was running, but unfortunately when generating the grasps for objects that were not known and we didn't know where's the location, the location of the object, sorry, sometimes the object was slipping from the fingers. And so when we wanted to place it, the object was misplaced because the object was slipping from the fingers. So we try to close the loop through a slip detection module that we've implemented previously for the U-Skin sensor by Xela Robotics. And it really helped us to come up with a precise placing pipeline. So here's a video of the whole process. Of course, it's a bit sped up for a gain of time. You'll see the graphical user interface. So the first step is to describe the robot, use a URGF file, say how do we want to launch the tactile sensor. Here, we basically want to explain how to communicate with the robot arm and how to control it, so basic ROS controller. Here we use a controller for the gripper that is provided by the gripper manufacturer, so Sake Robotics. And so we don't need to know how it works behind the scenes. We just say, oh, use this service that has been provided by the company. Here we set up the whole robot. Here what we're currently doing is configuring an RGBD sensor to have an interface to collect the point clouds out of it and provide it to the next components later on. And the last bit is to define the high-level methods. So we have a vision grasping algorithm that has been extracted from GitHub. It had a survey that was running it and outputted 60 pose. So we just had to use this and just specify the file, and we don't know, once again, to know how it works, like how the code works. And the slip detection module that we've developed ourselves, and you'll end up on this kind of interface. So you see the different states on the right that have been added due to our configuration. Here we want to get a point cloud from the Kinect 2 provided to the vision-based grasping algorithm that will output, as I said, a 6D pose that will be sent to move it. So we're going to move there, close the fingers, and then, so basically execute the grasp. And here, exactly here, we have the slip detection module. So depending on the outcome of the slip detection module, so if no slip here is detected, then we're going to execute a very precise trajectory to place the object where we want to. But if a slip is detected, then we're going to place the object back to where it was, move the arm away from the Kinect, and just reproduce the whole pipeline. So meaning recollecting the data point clouds, regenerating the grasp based on vision, and repeat until we have proper behavior. So here we launch the robots, and this is the execution time. So a grasp is generated from the point cloud that you've just seen. The grasp is executed. The object is slipping, so we place it back. We move the arm away. A second grasp is generated from the updated point cloud. We get the no slips that is detected, and we'll be able to really accurately place the objects. So that's all for me. Here are the references of the grasp pose detection algorithm we've used, the tactile module we came up with that has been published in IROS this year. If you want to know more about the grip, you have the documentation here. And if you want also to know more about even a user study, you have the paper that has been published to run. Thank you very much.